Use the second form of curvature to compute kappa, the curvature, for the space curve r of t equals 3/2 t squared, comma, t times the square root of 6, comma, natural log of 2t. And because of the natural log here, t has to be bigger than 0. Now the first form of curvature was kappa equals the magnitude of the derivative of the unit tangent vector with respect to s, which is the arc length parameter. So in this scenario, we were assuming that we had the curve in the form r of s, where s is an arc length parameter, and then that means that the magnitude of r prime of s is just 1, so that we have a curve of constant speed 1. Curvature, we want to measure how much the tangent vector is changing in its angle, not in its length or in its speed. So we would like the parametrization of the curve to be normalized, constant and speed 1. And then this derivative is measuring a rate of change, and the only thing that's changing is the direction of the tangent vector. So that tells us the curvature. Okay, now the second form, sometimes it's hard to write the curve in terms of the arc length parameter, which is the case here. Let me comment on that briefly. There's a formula for computing the arc length parameter, and in the problem that we have here, I've computed s to be 3t squared over 2 plus the log of t. And then to convert to the arc length parameter, we would have to solve this equation for t. So we would have to invert this equation, and that's not something that we can do. So the first method for finding curvature using the arc length parameter is out the window. Fortunately, there are a few ways to express the curvature formula, and the second way is using any parameter, t for the curve, and then the magnitude of t prime of t divided by the magnitude of r prime of t. So we still have to work with the unit tangent vector, but this time, because it's not because the parameter is not an arc length parameter, we have to divide here by the magnitude of r prime, the speed of the curve. Notice that if this t were an arc length parameter, then these would be exactly equal, because this is nothing other than t prime of s. And so if t was an arc length parameter, this would exactly be that, and then this would be 1. So the second form does agree with the first form in the case that the t is in fact an arc length parameter. Okay, so let's go about using this formula, because again, the arc length parameter for this curve is not easy to transition to. So we will deal with this one. So let's calculate r prime of t, and let's first also, t of t, the unit tangent vector, is r prime of t divided by the magnitude of r prime of t. So we need r prime of t in 2 places in this formula. 1, we see it here on the bottom, and 2, t prime of t has r prime of t, the magnitude of r prime of t, hidden in it. So these are vectors, and let's calculate r prime of t. So r prime of t, here's r of t. R prime of t is the vector 3t square root of 6. And then here we have to use the chain rule. For the logarithm, it's going to be 1 over 2t times 2, which is 1 over t. So this is r prime of t, and then the magnitude of r prime of t is the square root of the sum of the squares of the components. The square of 3t is 9t squared, plus the square of the square root of 6 is 6, plus the square root of 1 over t is 1 over t squared. Now this expression is itself a perfect square. This is 3t plus 1 over t quantity squared. You can double check that. And so this square root is 3t plus 1 over t. Now we might want to put that in absolute values, but we are insisting that t is positive, and so this is a positive quantity. In general, the square root of a number squared is not the number, but the absolute value of the number, because the x here could have been negative. But okay, 3t plus 1 over t is positive, because t is positive, so no need for absolute value bars. Now, t of t itself is r prime over the magnitude of r prime. So here's r prime, and here's the magnitude of r prime. So we have to divide each of these components by this. So that means we have to multiply by 1 over 3t plus 1 over t. And we can make that look a little nicer by multiplying by t over t to get t over 3t squared plus 1. So that's 1 over the magnitude of r prime. So that's this guy here on the bottom. So we have to distribute this fraction across r of t. So t of t is 3t times this fraction, which is 3t squared divided by our denominator, and then square root of 6t, or t root 6, over the denominator, and then 1 over t times this fraction. The t's cancel, and you get 1 over the denominator. Okay, so there's our unit tangent vector. Now we have to take the derivative of that and divide it by r prime of t again. So we're going to take the derivative of t and multiply it by this fraction, because this is 1 over the magnitude of r prime. So what is t prime? We're going to need to break out the quotient rule a little bit here. So let's make this big. On the bottom of the first one, we have 3t squared plus 1 squared, and that's going to be the case for all of these. So let me rewrite this here. 1 over r prime of t is t over 3t squared plus 1. We need that, but it's in the way of our upcoming derivative here. The second fraction is also going to have 3t squared plus 1 squared, and the third fraction is also going to have 3t squared plus 1 quantity squared. Now the numerators, it's the bottom times the derivative of the top minus the reverse. So 3t squared plus 1 times 6t minus 3t squared times 6t. And that all shakes out to be just 6t. Because the 3t squared times 6t minus 3t squared times 6t cancels, and we're just left with the 6t times 1. On the top, we have a square root of 6, which I'll factor out. And then the bottom times the derivative of the top is 3t squared plus 1 times 1. And then minus t times the derivative of the bottom is t times 6t, which is 6t squared. And so in the brackets, that's 1 minus 3t squared. And for the last one, it's the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, so it's minus 1 times 6t. So that one was friendly. Okay, so there's t prime of t. Now we need the magnitude of that. So the magnitude of t prime of t is, now the t prime of t, we could just factor this number off at the bottom. So let's do that. So this is 1 over 3t squared plus 1 squared, which is a positive number. So we don't have to take the absolute value of it. And then times the magnitude of the vector 6t, 1 minus 3t squared minus 6t. And this is 1 over 3t squared plus 1 squared times, and now this magnitude is the square root of the sum of the squares. This is going to be 36t squared, and this one's also 36t squared, so that's going to make 72t squared plus the square of this one, which is 1 minus 6t squared plus 9t to the fourth. And I missed my square root of 6 here, so there was also a square root of 6 here, right there, times this quantity here, so this should be 6 times this. 6 times this. So this should be a 6, this should be a 36, and this should be a 54. All right, let's just erase that. So I dropped this square root of 6 here in our numerator. So our numerator was the square root of 6 times this quantity. So when we square it, we get 6 times what I had written before, and that was 6 minus it was, before it was 6t squared, now it's 36t squared, and 9t to the fourth becomes 54t to the fourth after multiplying through by the 6. Okay, now this simplifies. This problem was carefully constructed so that all of the algebra works out smoothly, because there's a ton of it. 1 over 3t squared plus 1 squared times the square root of this is 6 plus 36t squared, because we have a negative 36 and a plus 72t squared. So combining those two, we get a plus 36t squared and then plus 54t to the fourth. And this is 1 over 3t squared plus 1 squared times the square root of 6, factoring out a 6, times the square root of 1 plus 6t squared plus 9t to the fourth, and that's a perfect square. This guy is 1 plus 3t squared quantity squared, and so this is the square root of 6 over 3t squared plus 1 quantity squared times 1 plus 3t squared, and this is the same as that, so this cancels with one of those. We get the square root of 6 over 3t squared plus 1. So that's not our final answer. That was t prime of t. That was the magnitude of t prime of t. So remember, the formula kappa was the magnitude of t prime of t divided by the magnitude of r prime of t. So now we have the numerator of that. It's this fraction, square root of 6 over 3t squared plus 1. And now we have to divide that by the magnitude of r prime of t, which was, happens to still be on the board, it was this. And we have to divide by that, which means we have to multiply by 1 over it. So this is, so we can think of this as t prime of t times 1 over r prime of t magnitudes. And when we did the reciprocal of this one, it was, so we have to multiply here by this reciprocal, which was t over 3t squared plus 1. And I believe if I scroll up, we can see that. There was r prime of t, magnitude, and there's 1 over the magnitude of r prime of t. So t squared over 3t squared plus 1. So this is our final answer. And we can write this as t root 6 over 3t squared plus 1 quantity squared. So that is our curvature. We do not have constant curvature for this particular space curve. The curvature changes as we move along the curve. So for example, when t is equal to 1, that gives us that the curvature kappa at 1 is the square root of 6 divided by 16. If I did that right, put in a 1 there, 3 plus 1 squared, 16. So really we should think of kappa as being kappa of t. It's not generally a constant. In the first few examples, it was a constant, but here we see that it depends on t. Kappa of 2 is 2 times the square root of 6 divided by 169. I believe that's a 13 there. 4 times 3 plus 1. And so this is not the same as the square root of 6 over 16. They're different. So the curvature is changing from point to point. All right, so that was the second form of curvature. The first form, which gives you the concept of curvature, we want a tangent vector to our curve that has constant length, and we want the curve moving at constant speed. We want the curve moving at not just constant speed, but at the same speed for all curves. So speed 1 will work. So that's the arc length parameter does that for us. But in many cases, the arc length parameter is not something that we can convert into, like in this case, where we knew what s was equal to, but we could not substitute that in here because we would have to solve this equation for t. So we have this second form of curvature, which does not require us to use the arc length parameter, but it certainly agrees with the first formulation in the case that the parameter is the arc length parameter. And a proof that they're actually equal just hinges on the chain rule. So we use this second form for this curve here, and we got an answer.